Good afternoon, reliability and maintenance professionals everywhere. It is my pleasure to speak to you today, and I'd like to thank ISRA Engineering for giving me such fantastic opportunity for the second time to learn from other SmartCon speakers and to share my thoughts as well, as I had unforgettable memories during the SmartCon 2019. So despite the fact it was a busy time when I received the SmartCon's 2020 invitation, I was not able to resist, and I remember the fantastic quote says, "Nobody's busy, it's just a matter of priorities." So I believe that one of the first things we should do every day morning is setting our priorities before scheduling the daily activities. When it comes to our asset management effort, the concept remains the same. So for any plans, we have to prioritize short-term tasks as well as our long-term projects. But considering the massive number of assets we have, running the plans without knowing the priority of each task will result in conflicting priorities that increase our waste and also reduce productivity and decrease reliability. So in the end, remember, the key is not to prioritize what's on your schedule, but to schedule your priorities, right? So this presentation aims to help organizations set their priorities based on asset criticality assessment approach, uses a decision-making grid. The material is based on a research paper within the Journal of Quality and Maintenance Engineering, in which we try to propose a streamlined approach that delivers almost the same criticality results when used by different groups, also helps organizations sailing through the current dynamic business environment, right? So it was my honor to collaborate in this work with Mr. Labib, the Professor of Operations and Decision Analysis at the University of Portsmouth, and I would like to thank him for his contribution to this work. So let's ask the question, why do we need to assess the criticality of our assets? Or in other words, why we have to dedicate resources and to spend time in this lengthy exercise, right? So as said at the beginning, we need to know the criticality of our assets in order to prioritize our day-to-day activities, such as work orders, and also to prioritize improvement optimization projects, such as selecting which assets should we perform RCM, which assets should we perform FEMIA, which assets for RAM modeling, and so on. And also to stay focused on the performance of the most critical assets. So I have seen many organizations creating a dedicated key performance indicators that focus on the most critical assets based on taxonomy or based on allocation, right? So you can see a key performance indicator like the mean time between failure for critical A assets or for critical A centrifugal pumps, right? So having the criticality in place helps organization to create those kind of custom KPIs that help people to stay focused in the most priority aspects. Another part of the story here is why we need to have an agile approach in doing our asset criticality assessment. So as you know, the business environment becomes more dynamic nowadays as a result of this accelerated move towards digital transformation and the Internet of Things. So for companies to sustain their existence, it is vital to stay focused on and set priorities for improvement in a more agile way, right? So as maintenance and cost and asset management costs represent a significant percentage of the company's operating costs, then the optimization of maintenance and asset management efforts will definitely result in an overall optimization of the company's performance and, of course, a significant increase in the profit margin, right? So this optimization will not be possible without having the right priorities in place. And of course, our priorities change as the operating context changes, right? So here, remember this quote, right? It is not the strongest species that survives, nor the most intelligent, but the most responsive to a change, right? So now let's speak about this approach for asset criticality assessment using decision-making grid. So the idea here, we break down the asset criticality assessment process into 3 stages or 3 components. The first stage, we call it the inherent criticality assessment, in which we consider factors related to design, related to configuration, related to the installation of the asset. Then we move to the second stage. So within the second stage, which we call it the achieved criticality, we assess our effort or how our efforts are influencing the inherent criticality of the assets, and it changes something like the mean time between failure of the assets. The last stage here, we consider the HSE consequences of assets worst case failure scenario on the achieved criticality at stage number 2, right? To understand this better, let's have an example, simple example to explain. Let's assume that we have this unit in place and we would like to assess the criticality of each system, right? So first, we start with the inherent criticality assessment. So we're gonna take one system as example. And in this exercise, we consider 2 components. We'll consider asset configuration and asset utilization as 2 dimensions of the inherent criticality. And for each dimension, we have defined few levels, right? So for asset configuration, we defined 4 levels. For asset utilization, we provided 5 levels, right? So then, considering the system we have selected here, so as per the information given, you can see that we have redundancy only. So the asset configuration will be number 3, level 3. And for the utilization, it's less than 60%. So we consider it as light utilization. This will be moved or mapped to what we call it a decision grid. So within the decision grid, we have 2 dimensions as well. And for each dimension, we have the number of levels. So putting this on the decision grid, it will end up and telling us that this system falls in cluster or cluster number 4, right? So we have here in this decision grid, we have 4 clusters: red cluster, orange cluster, yellow, and at the end we have the green cluster. So from the inherent criticality perspective, it falls in the green cluster. So now we apply the same on other systems in place. So when you apply the same concept on other systems, it will give you the inherent criticality of all other systems, as you see on the table at the just beside the diagram. Then the next level here will start the assessment of the achieved criticality. So within the achieved criticality, what we're gonna do here is, so we move forward to this second stage. So we use the achieved criticality decision-making grid. So, and to build up on what we have from the inherent criticality. So the inherent criticality will be result or outcome will be input to the achieved criticality decision-making grid, right? In addition to that, we'll add one more dimension here, which is the MTPF. So the mean time between failure will be an input to the second decision-making grid for the achieved criticality. And based on that, we can see here, as a result of our inputs, this achieved criticality of this system will be in cluster number 3 or in the yellow cluster, as you can see, right? Then we'll move to the third stage here, right? Or by the way, we can continue also assessment of the other system, and then we'll move to the third stage. So within the third stage, we'll consider the outcomes of the achieved criticality, right, as input to the third decision-making grid here. And beside this outcome, we'll consider inputs from the HSE consequences here. So considering the input from the HSE consequences, we can have this result which says that the criticality of this equipment falls in the yellow cluster. As you see here, we are moving from one stage to another stage, and we have grouped the factors that affect the criticality based on how far these factors are inherent or how far these factors are related to our effort, our work, or it's related to some factors we can say it's not fully under our control. By applying the same to other systems, you can see here, this is the criticality distribution of our system in this table provided in the slide. So as you can see in this slide, we have assessed the criticality at 3 stages. In case of any changes in the operating context, the criticality can be adjusted smoothly, right? This adjustment can be made by modifying the corresponding dimension. So you can change, if you increase the utilization, you can increase the level in the utilization dimension, and this will impact the criticality of the asset, right? Or if you have changed the configuration due to a redesign, then you can change the level of the asset in the asset configuration dimension, and this will impact the final criticality of the asset. These kind of changes can be done manually, or we can take it to another level by making some integration with other asset management systems in place. So this kind of things can be done through a specific logic or a specific type of AI in place. So it can change the criticality of the assets automatically. And as a result, the priority of our work on site can be changed correspondingly. Now let's discuss the strengths and challenges in this approach, right? So first of all, what are the strengths of this approach? It's time optimization is one, time and effort optimization is one of the first things, right? So as the decision-making grid dimensions and levels are clearly described, the time you need to complete this exercise becomes less, right? And the second thing I would like to speak here about is the standardization. The use of this decision-making grid reduces the variations when using different teams to assess assets criticality at different locations. So it tends to give us better standardization. It tends to reduce the variation when applied by different teams. Also, we have here easy decision-making, right? And that's why we said we are using a decision-making tool, and this is what we are doing here. So easy decision-making, as what you have seen here, it is a straightforward for the team to select the proper value in each decision-making grid with very high confidence in the outcome, right? And the last thing here is agility, or by applying this simple software here, as I explained in the previous slide, or even advanced artificial intelligence tools, the asset criticality assessment decision-making grid process can be fully automated. So to adjust the criticality of the asset as a result of any changes in the decision-making grid dimensions. Then what are the challenges we have? The first challenge here is the MTBF calculation. So the proposed approach assumes that you are using the right failure coding and the reporting in your CMMS. So the calculations of the mean time between failure will be at high quality, which is really not the case in many plants, because the reporting of the failure, it's not done at that level of quality that is needed to enable the optimization or enable the digitalization of the process itself, right? So having the right structure or RAM data quality in place is really needed to have this approach streamlined. Number 2 here is the clusters identifications. So how we'll identify the boundary of each cluster or the area of each cluster? How many squares should be per each cluster, right? This has to be done through one pilot run or one pilot implementation, try and the error and see what are the distribution. Also, it is not necessarily to have this thresholds at the beginning. You can complete the exercise, the full exercise, and then at the end, you can put the thresholds after you see the distribution of your assets. So by that way, you can guarantee that each cluster will have specific number of assets that depend on your business interest, right? Because again, putting the priority is dependent upon how much you are willing to invest. If you are willing to invest at unlimited amount of time and effort, then everything can be at high priority. But we are putting priorities because our resources, our willing to invest is not that much, so we cannot cover everything. Then I would like to discuss here the last point in my presentation here is the distribution of the asset criticality distribution. So if you look at this graph, you can see this number of assets on the vertical axis and the criticality on the horizontal axis. You can see here I have 4 clusters of criticality. So I have critical A asset, critical B asset, C asset, and D asset. And then we have the distribution in a blue line, right? So this should represent the expected distribution from the asset criticality exercise. The number of assets should be less as the criticality increase. So if, for instance, once you complete your exercise using your current asset criticality procedure in place, and once you finish your exercise, you found that some of the clusters in your asset criticality are not used, are not occupied by some assets. So then this should raise a question here, whether your procedure or whether the practices in place, the standard you are following is the right one, or you need to revise or review your strategy and your procedure and write a different procedure, change the thresholds, consider some other aspects, right? Because you cannot go by saying, I have 0 critical A assets. If you have 0 critical A assets, it doesn't mean anything then, because still you have to prioritize your things. If you do not have A category asset, then what should you do in this case, right? So here you need to review and update your criteria if this is the case. Then, as said at the beginning, the asset criticality assessment outcome should drive your or our optimization effort, right? So the low critical assets, for the low critical assets, you can spend minimum effort and time by considering options like run to fail, right? While for the most critical assets, we are willing to invest more time, more effort, so we can consider options like RCM for optimization, right? And for any of these options, RCM or FEMIA, or considering generic templates, the intention here is to consider asset by asset, and for each asset, you define or identify every single failure mode that seems reasonably likely to happen at the plant. And for each failure mode, you start doing the assessment again using your criticality assessment tool in order to say whether this failure mode needs to be mitigated by a certain mitigation action, or you can consider this failure mode as acceptable from the risk perspective, and you will not invest any money in mitigating such failure mode, right? So as you see here, we have like a big tree in the slide, and in order to collect all the fruits from this slide, we need to put the strategies in place in order to have the maximum outcome and the maximum utilization of all the tools you have in place, right? By this slide, this is the end of my presentation. So I believe still I have